You type a question into ChatGPT and press send. Almost immediately, words begin appearing on the screen. It feels as if the answer was already waiting somewhere inside your phone. It was not. Your prompt has just crossed networks, entered a data center, triggered an enormous mathematical model, and started a chain of calculations that predicts the reply one small piece at a time. The exact route and hardware can vary, but the hidden journey follows the same basic stages. The first stage begins before the prompt leaves your device. The app or browser packages your text into an internet request. A domain name lookup helps the device find the service, much like looking up a destination in a directory. Then an encrypted connection is established. Encryption does not make the request invisible to every system involved, but it protects the contents from ordinary eavesdropping, while the data travels between your device and the service. Your paragraph is divided into packets, small addressed pieces that routers can move across different networks. Those packets may leave through Wi-Fi or a mobile tower, enter your internet provider, and pass through several routers before reaching infrastructure serving ChatGPT. If the destination is far away, some of the physical journey can run through fiber optic cables on land or beneath the ocean. Light pulses carry data through glass strands. The packets do not need to follow one permanent road, and different packets can be routed differently when networks are congested or links fail. We cannot draw one universal ChatGPT route because location, provider, traffic, and system design all change it. Eventually, the request reaches a data center system. A data center is not one giant computer. It is a secured building filled with racks, power equipment, networking switches, storage systems, and cooling machinery. Front-end servers receive requests, check that they are valid, and direct work toward available computing capacity. Safety systems can also inspect the request and the generated output. Load balancers spread traffic so that one machine is not expected to answer everyone at once. The exact internal architecture used for a particular ChatGPT request is not publicly exposed and can change over time. Before the language model can work with your sentence, the text is divided into tokens. Tokens are the pieces of text the model processes. A token might be a whole short word, part of a longer word, a punctuation mark, or even a space pattern. This is why token counts do not perfectly match word counts. Your tokens are converted into numbers, and then into long lists of values called vectors. Those values represent patterns the model learned during training, allowing mathematical operations to compare relationships between pieces of the prompt. Now the heavy computation begins. Modern language models run on specialized accelerators, hardware designed to perform huge numbers of matrix calculations in parallel. Depending on the deployed system, that can mean graphics processors or other purpose-built AI chips connected by extremely fast networks. The trained model is already there. Answering your question is called inference. The system moves numerical data through many layers, repeatedly combining information from the prompt and the text generated so far. It is not searching a hidden book containing a finished answer. It is calculating what should come next. At each step, the model produces scores for possible next tokens. Those scores are turned into probabilities, and the system selects one token according to its settings and rules. Add that token to the conversation, run another step, select another token, and repeat. That loop is why an answer often appears progressively, instead of arriving as one finished page. The model can produce fluent explanations because it has learned extremely rich statistical patterns, but prediction is not the same as guaranteed truth. A plausible next token can still continue an incorrect idea. Tools such as web search, calculators, or code execution may be called for some requests, but they are additional systems, not magic knowledge inside every answer. As tokens are generated, the service can stream them back across the network rather than waiting for the entire response. The return journey again passes through networking equipment and internet links. Your device receives the encrypted data, verifies and reassembles the packets, and the app turns the tokens into the words you see. What looks like typing is really a sequence of small completed generations, arriving faster than the interface can comfortably display them. The first words can therefore appear, while later parts of the answer are still being calculated. All of that computation becomes heat. Chips use electricity, and almost every watt entering the computing equipment eventually has to leave as heat. Fans, pumps, heat exchangers, chillers, or liquid cooling loops move that heat away from the hardware. Some facilities use evaporative cooling, which can consume water. Others rely more heavily on air cooling, closed loops, or different designs. Water can also be used indirectly by the power plants that generate electricity. That is why there is no honest universal number for the water used by one ChatGPT prompt. Model size, answer length, batching, chip efficiency, local weather, cooling design, and the electricity mix can all change the result. The scale matters even when one short request feels tiny. The International Energy Agency estimated that data centers used roughly 1.5% of global electricity in 2024, and projected demand to more than double by 2030, with artificial intelligence as the largest driver of that growth. But a global data center total is not the footprint of one question, and ChatGPT is only one service inside a much larger industry. The useful lesson is not that every prompt has one dramatic fixed cost. It is that a seemingly weightless digital action depends on physical buildings, grids, cooling systems, cables, and manufactured chips. So when you press send, your question does not disappear into a cloud. It becomes packets, crosses a network, is converted into tokens, flows through layers of mathematical operations, and returns as a stream of newly selected pieces of text. The entire process can begin producing an answer in seconds because every layer, from fiber routes to accelerator chips, has been engineered for speed and enormous scale. The screen shows only a conversation. Behind it is one of the most complex industrial systems most of us use every day.